Time. It is the one thing we all move through, yet never touch. We measure it in seconds, but feel it in memories. We chase it, waste it, fear it, and yet we know so little about what it truly is. We live our lives on a tiny speck of dust, floating in an incomprehensibly vast universe. A universe that began in fire, that stretches in silence, that holds secrets buried in the very fabric of space itself. And at the center of it all, time, the silent witness to everything that has ever existed and everything that ever will. But what if time isn't what we think it is? What if the laws that govern the falling of an apple also explain the birth of galaxies? What if everything we believe about beginnings and endings is wrong? Stephen Hawking dared to ask these questions. In this series, we journey through his most profound work, A Brief History of Time. This is not just science. It's a quest to understand reality itself. So pause, breathe, and let go of everything you think you know, because we are about to step into the deepest mysteries of the cosmos. And it all begins with time. Chapter 1. Our Picture of the Universe. From a moment human beings looked up at the night sky, they've asked the same question. What is this place? What is the universe? And where do we fit in? Long before telescopes, long before science, humans told stories, myths, legends. We imagine gods throwing stars into the sky, or great cosmic turtles carrying the earth on their backs. These stories gave meaning, but they lacked something else, predictability. Then came observation, curiosity, pattern. The ancient Greeks were among the first to try and explain the cosmos using reason. Aristotle believed the earth was the center of the universe, with the sun, moon, and stars rotating in perfect circles around it. It felt obvious. The ground beneath your feet doesn't move. The stars seem to spin around you. Why wouldn't Earth be the center? But the heavens refused to behave. Planets would slow down, reverse direction, and then resume their path. To account for this, the Greek astronomer Ptolemy developed a system of epicycles, tiny circles upon circles to make the math work. This model wasn't right, but it was useful. For over 1,400 years, it guided navigation, calendars, and astronomy. Then, in the 16th century, everything changed. Nicholas Copernicus proposed something radical. What if the sun, not the earth, was at the center? At first, his idea was dismissed, even dangerous. But then came Galileo Galilei, who built a telescope and pointed it skyward. He saw moons orbiting Jupiter, evidence that not everything revolved around Earth. His observations challenged the very foundation of human understanding. For that, he was silenced, forced to recant. But the truth had already escaped. Johannes Kepler added to the revolution, showing that planets move not in perfect circles, but ellipses. And finally, in the 17th century, Isaac Newton arrived and changed everything. Newton's genius wasn't in merely observing the heavens. It was in connecting them to Earth. He discovered that the same force that pulls an apple from a tree also keeps the moon in orbit. That force was gravity. With his laws of motion and universal gravitation, Newton gave the universe structure, a system, a set of rules that applied everywhere, always. For the first time, we had a model that could predict the movement of planets, moons, comets, even the tides. And for centuries, that model held. Newton's universe was a machine. Precise, predictable, eternal. But there was a problem, a subtle one. His laws worked beautifully for most things, but not everything. The deeper scientists looked, the more cracks began to appear. For instance, Newton's physics couldn't explain the odd orbit of Mercury, and it treated time and space as fixed backgrounds, unchanging stages upon which the universe played out. What if they weren't fixed? What if time and space could bend, stretch, or ripple? It would take another genius, Albert Einstein, to shatter that certainty. And in doing so, he would open the door to an entirely new way of thinking about time, space, and the universe itself. But before we follow Einstein into the curved corridors of space-time, let's pause. Because here's what matters. From Aristotle to Newton, we see a pattern, not just in the cosmos, but in the human mind. A relentless drive to understand the unknown, to look at the stars not with superstition, but with wonder sharpened by reason. And yet, every time we think we've grasped the full picture, the universe humbles us. What we see is not always what is. And the deeper we look, the stranger things become. In the next chapter, we'll explore what Einstein discovered and how he proved that time is not absolute. It flows, it bends, and it might not be what we think it is at all. Chapter 2, Space and Time. Imagine standing on a train platform. A train speeds by, and a passenger aboard drops a ball. To them, the ball falls straight down. But to you, watching from the platform, it follows a diagonal path. Same event, different perspectives. This simple thought opens the door to one of the most profound truths in modern physics. Space and time are not absolute. They are relative. For over 200 years, Newton's idea of absolute time and space reigned supreme. Space was the fixed arena in which matter moved. Time ticked uniformly, like a divine clock set at the beginning of creation. But in the early 20th century, that certainty was shattered by a man who thought in paradoxes. Albert Einstein. In 1905, Einstein proposed a new way of looking at motion, the special theory of relativity. Its two main assumptions were deceptively simple. 1. The laws of physics are the same for all observers, no matter how fast they're moving, as long as they're not accelerating. 2. The speed of light in a vacuum is always the same, regardless of how fast the source or observer is moving. These statements seem innocent, almost boring, but their implications are anything but. Because if the speed of light is constant, then something else must give way. That something is time. Let's break it down. The death of absolute time. Imagine two lightning bolts strike both ends of a moving train. To a person standing on the platform, equidistant from both strikes, they appear to happen simultaneously. But to someone on the train, moving toward one bolt and away from the other, the timing shifts. They might see the front strike before the rear. Or vice versa. Which observer is right? Both. There is no single objective now that the universe agrees on. Simultaneity is relative. This isn't just a thought experiment. It's built into the fabric of reality. According to Einstein, time slows down the faster you move. This phenomenon is called time dilation. We've measured it. Astronauts on the International Space Station age slightly slower than people on Earth. Not by much, but the effect is real and measurable. Even GPS satellites must account for this. Without relativistic corrections, their positioning systems would fail. This isn't science fiction. This is how our world actually works. Length contraction and mass increase. But time isn't the only casualty of high-speed motion. As objects move faster, they also contract in length from the point of view of a stationary observer. This is called length contraction. And that's not all. As an object accelerates closer to the speed of light, its mass increases. Eventually, it would take infinite energy to push it to light speed. That's why nothing with mass can reach the speed of light. Light, traveling at the cosmic speed limit, is reserved for massless particles like photons. For massive things, like you and me, light speed is an eternal horizon, forever out of reach. Space and time, a single fabric. Now here's the leap. Einstein realized that space and time are not separate entities. They are intertwined, woven together into a single continuum called space-time. This idea didn't just explain how time dilates or how length contract. It changed our entire view of the universe. Time is not just a ticking clock. Space is not just a silent void. Together, they form a dynamic stage that reacts to mass and energy. In Newton's universe, gravity was a force acting at a distance. In Einstein's universe, gravity is geometry. Mass tells spacetime how to curve, and curved spacetime tells objects how to move. Let that sink in. Beyond special relativity. Einstein's special relativity dealt only with observers moving at constant speeds, no acceleration. But the universe is full of acceleration. Planets orbit. Rockets launch. Stars explode. So in 1915, Einstein extended his theory and created something far more ambitious. The general theory of relativity. It would explain gravity, not as a force, but as a warping of the space-time fabric itself. It would predict black holes, gravitational waves, and the bending of light. But we're getting ahead of ourselves. Before we dive into gravity and the warping of reality, let's reflect on what we've learned so far. The collapse of the common sense world. Our everyday experience tells us that time is steady, that rulers don't shrink, that mass stays constant. But the universe is not beholden to our intuition. Reality doesn't care how things feel. Time moves differently depending on how you move. Distances are not absolute. Even now is not universal. We're left with a universe that is far stranger than we ever imagined, but also far more beautiful. A universe where everything is connected. Motion affects time. Gravity bends space. And light, the cosmic speed limit, remains ever constant. In the next chapter, we'll zoom out. We'll look not just at motion, but at expansion. Because it turns out the universe is not still. It is stretching, growing, and it may have had a beginning. In Chapter 3, we dive into the expanding universe. Chapter 3, the expanding universe. We often imagine the universe as eternal and unchanging, an infinite stretch of stars scattered through the cold silence of space. But that illusion of stillness is just that, an illusion. The truth is, the universe is alive with motion. Not the motion of stars drifting or planets spinning. Those are local. We're talking about something much grander. The fabric of space itself is stretching. This chapter tells the story of that cosmic revelation, of how we learned that the universe had a beginning, and that it's still growing. The universe, once thought static. For centuries, the dominant belief was that the universe was static and eternal. Even Albert Einstein, when he applied his equations of general relativity to the universe as a whole, found something strange. It didn't want to stay still. Gravity pulled everything inward. So, a universe full of matter should collapse on itself. But that didn't match what people assumed to be true, that the universe was eternal and unchanging. To fix this, Einstein inserted a term into his equations, the cosmological constant, a kind of anti-gravity force that would counterbalance gravity and hold the universe in a delicate balance. Later, he would call this his greatest blunder, because soon, observations would show that the universe was not static. It was expanding. The discovery of the expansion. The first hint came from a man staring at the stars with a giant telescope in California. In the 1920s, Edwin Hubble, using the 100-inch Hooker telescope at Mount Wilson Observatory, studied the light from distant galaxies. What he found would change everything. Light from these galaxies appeared redshifted, stretched toward the red end of the spectrum. What does that mean? It's similar to the Doppler effect, where the pitch of a siren lowers as it moves away from you. In light, stretching the wavelength makes it redder. The more distant the galaxy, the more redshifted its light. That meant those galaxies weren't just drifting, they were receding, flying away from us. And not just randomly, but systematically. The farther away a galaxy was, the faster it seemed to be moving away. This wasn't just local motion. This was the expansion of the universe itself. Space wasn't a stage where galaxies moved. Space was expanding, and the galaxies were moving apart because of it. This became known as Hubble's law, and the slope of that line, the rate at which space expands, is called the Hubble constant. The implication, a beginning. If the universe is expanding now, then in the past, it must have been smaller. Rewind the clock far enough, and what do you get? A point, a moment, a singularity, a time when all matter and energy were compressed into an infinitely dense state. This wasn't just a theory. It was a natural consequence of general relativity and Hubble's observations. The idea that the universe had a beginning, an origin in time, was now on the table. And that idea would evolve into what we now call the Big Bang Theory. What the Big Bang is, and isn't. Let's clear something up. The Big Bang wasn't an explosion in space. It was an explosion of space. It didn't happen at one point in space. It happened everywhere simultaneously, because back then, all space was compressed into a single point. When the Big Bang occurred, space itself expanded. There was no outside to expand into. There was no before the Big Bang, because time itself began with it. That's hard to wrap your mind around. But remember, time and space are part of the same fabric, space-time. Before the Big Bang, there was no space-time, no before to speak of. The afterglow of creation. Is there any evidence of this beginning? Yes. And it came from a pair of radio engineers in New Jersey, Arno Penzias and Robert Wilson. In 1965, while trying to eliminate noise from their radio antenna, they stumbled upon a faint, persistent hiss coming from every direction. They had discovered the cosmic microwave background radiation, the faint glow left over from the Big Bang. This radiation is a snapshot of the universe just 380,000 years after its birth, when atoms first formed and light was free to travel. It's the oldest light in the universe, the echo of creation itself, and its uniformity across the sky confirmed that the universe began in a hot, dense state and has been expanding and cooling ever since. The universe's fate, will it end? If the universe is expanding, what happens in the future? Will it expand forever? Or will gravity one day halt the expansion, reverse it, and cause a big crunch, a cosmic collapse? The answer depends on the total amount of matter and energy in the universe. If there's enough mass, gravity will win. If not, expansion continues forever, perhaps even accelerating. Today, observations suggest the expansion is not slowing down. It's speeding up. A mysterious force called dark energy is driving this acceleration. And so, the universe may expand forever, growing colder, emptier, darker, in a long, slow fade into cosmic isolation. We will explore this in much more detail later. The cosmic tapestry. Let's pause for a moment. Think about it. We, small creatures on a pale blue dot, have uncovered evidence that the entire universe had a beginning. We've seen its glow, measured its stretch, felt its pulse. Through the lens of physics and mathematics, we've rewritten creation stories once told by campfire and candlelight. This isn't just science, it's poetry at the largest scale. It shows us that we are not the center of the universe, but we are central in understanding it. We are the cosmos becoming aware of itself. And as we stare deeper into the abyss of time, we begin to wonder, what is time? How can something begin if time itself began? In the next chapter, we'll tackle that question head-on. We'll dive into quantum uncertainty and the strange world of probabilities that lies beneath everything. Chapter 4. The Uncertainty Principle. At first glance, the universe seems orderly. Planets orbit the sun with precision. Apples fall from trees. Clocks tick in rhythm with the laws of Newton. It's a comforting picture, a universe where everything happens with purpose and predictability. But that certainty vanishes when we look closer. At the tiniest scales of nature, the world becomes strange, uncertain, blurred. This is the realm of quantum mechanics. And at its heart lies a radical idea. You cannot know everything about a particle at once. Not its exact position and its momentum. Not its energy and the precise time that energy exists. There is a fundamental limit to what we can know. This is Heisenberg's uncertainty principle, and it changes everything. The death of determinism. In classical physics, the future was fully determined by the present. If you knew the position and velocity of every particle, you could predict the entire future. Laplace, a French mathematician, imagined a vast intelligence that knew every detail of the universe at a moment. To it, nothing would be uncertain. But quantum mechanics shattered that dream. Uncertainty isn't just a matter of ignorance. It's built into the universe itself. The more precisely you try to measure a particle's position, the less precisely you can know its momentum, and vice versa. This isn't due to faulty instruments. It's because particles don't have precise values for both at the same time. They are not little balls bouncing around like marbles. They behave like waves and particles at once. Fuzzy, probabilistic, undefined until observed. In other words, reality doesn't exist in a definite way until we interact with it. waves, particles, and probabilities. Think of an electron. It's not like a tiny planet orbiting a nucleus. It's more like a cloud of possibilities, a shimmering fog of where it might be. Only when we observe it does it collapse into a specific location. Before that, it's all probabilities, a wave of likelihood. This wave is described by something called a wave function, developed by Owen Schrödinger. It doesn't tell us where the particle is. It tells us where it's likely to be found. Quantum mechanics is not about certainty. It's about chance. The entire fabric of reality, at its core, is probabilistic. And that makes the universe unpredictable, not in a chaotic sense, but in a way that no amount of knowledge can fully overcome. The double-slit experiment. To grasp how strange this really is, consider one of the most famous experiments in physics, the double-slit experiment. Imagine firing tiny particles like electrons at a barrier with two slits. Behind the barrier is a screen that lights up where electrons hit. If electrons were just particles, we'd expect to see two bright spots matching the slits. But instead, we see an interference pattern, as if waves are overlapping, creating bright and dark bands. Now here's the twist. Even if you fire the electrons one at a time, they still create an interference pattern, as if each electron goes through both slits at once, interfering with itself. It behaves like a wave, but when you observe which slit it goes through, the interference pattern disappears. It behaves like a particle. The act of observation changes the outcome. This experiment, repeated countless times, reveals something unsettling. At a quantum level, reality responds to being watched. The uncertainty principle and energy. The uncertainty principle doesn't just apply to position and momentum. It also applies to energy and time. There's a limit to how precisely you can know both. This has a wild implication. For very short moments of time, a particle can borrow energy from nothing. Particles can briefly pop into existence, then vanish again. These are called virtual particles. They can't be observed directly, but their effects are measurable. This is not science fiction. It's quantum reality. It even helps explain phenomena like Hawking radiation, which we'll explore later. At the smallest scales, the vacuum of space is not empty. It's boiling with flickers of existence and annihilation. A restless quantum sea. The end of absolute knowledge. So what does this all mean? It means we must give up on the idea of absolute knowledge. The dreams of perfect prediction, of a universe as a great clock, are gone. Instead, we enter a new way of thinking. The universe is not deterministic, it is probabilistic. And yet, it's still governed by laws. Quantum mechanics doesn't allow us to say what will happen, but it tells us what is most likely to happen. And those predictions are incredibly accurate. They explain the structure of atoms, why the sun shines, how chemistry works, why life exists at all. Uncertainty is not a bug in the system. It is the system. Chaos at the core. As we zoom out from the quantum world back into the realm of stars and galaxies, you might wonder, if everything is uncertain down there, why does the universe look so stable up here? The answer is scale. On average, over huge numbers of particles, the uncertainties cancel out. The world of everyday experience is shaped by the laws of classical physics, because quantum effects are small. But when we push to extremes, inside black holes, at the moment of the Big Bang, in particle accelerators, quantum uncertainty reigns supreme. And in those realms, our current theories, general relativity and quantum mechanics, begin to clash. They are both incredibly successful, but they do not play well together. Reconciling them is one of the greatest challenges in physics today. And that journey begins with a singular question. What happens inside a black hole? Chapter 5. Elementary Particles and the Forces of Nature. We often think of the universe as something vast and distant, stars, galaxies, planets drifting through a cosmic sea. But Stephen Hawking asks us to shift our gaze inward, because before we can understand the grand architecture of space and time, we must understand its smallest components, the elementary particles, the tiniest bricks of existence, the alphabet of the cosmos. From the outside, the world appears continuous, fluid, and solid. But dive deep, deeper than molecules, deeper than atoms, and you enter a world that defies ordinary logic. A world where particles aren't truly particles, where energy and matter become interchangeable, and where forces act not through contact, but through invisible exchanges of ghost-like messengers. This chapter is our map into that unseen territory. The road to the invisible. Once, scientists believed atoms were the smallest indivisible units. The word itself comes from the Greek atomos, meaning uncuttable. But as experiments grew more precise in the early 20th century, it became clear atoms are not the end. They are the beginning. At the heart of every atom is a nucleus made of protons and neutrons. Surrounding the nucleus is a buzzing cloud of electrons, occupying regions of space defined more by probabilities than by clear orbits. But what are protons and neutrons made of? The answer is found in a strange, more fundamental layer of reality: quarks. Quarks are the true building blocks. A proton consists of 2 up quarks and 1 down quark. A neutron, 1 up and 2 down. These combinations are held together by an incredibly powerful interaction known as the strong nuclear force. Yet even quarks do not act alone. They are accompanied by a vast family of other particles: electrons, neutrinos, muons, bosons, each with unique properties and roles. To understand their behavior, we need to understand not only what these particles are, but how they interact. The 4 fundamental forces. In the particle world, matter is only half the story. The other half is interaction. The forces that bind particles together, push them apart, and shape the universe from the subatomic to the cosmic scale. Physicists have discovered that all interactions in nature fall under 4 fundamental forces. 1. Gravity. We feel it every second of our lives. It keeps our feet on the ground, binds the moon to the earth to the sun, and the sun to the spiral arms of the Milky Way. It shapes the orbits of galaxies and bends the very fabric of space-time. And yet, it is the weakest of the 4 forces. A tiny magnet can lift a paperclip against the gravitational pull of the entire Earth. Despite its weakness, gravity is dominant on cosmic scales because it always attracts and never cancels out, unlike electric forces, which can be positive or negative. Einstein redefined gravity in his general theory of relativity, not as a force pulling across space, but as the warping of space-time itself. Massive objects bend the fabric of the universe, and smaller objects move along the curves. And yet, at the particle level, gravity is almost irrelevant. It is not part of the standard model, and that makes it the biggest outlier in modern physics. 2. Electromagnetism. Next comes the electromagnetic force, which acts between charged particles. It's responsible for light, for electricity, for magnetism, for chemistry. It's what binds electrons to nuclei. It's the reason atoms exist. This force is carried by a massless particle called the photon. Photons travel at the speed of light because they are light. When electrons accelerate or shift energy levels, they e. These particles have no mass and no charge, but infinite reach. Without electromagnetism, there would be no light, no matter as we know it, no life. 3. The strong nuclear force. Inside the nucleus of every atom, protons, which are positively charged, sit tightly packed. According to electromagnetism, they should repel each other violently. So why doesn't the nucleus explode? Because the strong nuclear force holds it together. It's the most powerful of the 4 forces, about 100 times stronger than electromagnetism. But it acts only at incredibly short distances, about the width of a proton. This force is carried by particles called gluons, which act like springs between quarks. Gluons don't just bind quarks together. They also carry color charge, a quantum property that ensures quarks are always bound in groups. No quark has ever been observed in isolation. This phenomenon is called confinement, one of the defining features of the strong force. 4. The weak nuclear force. This is the strangest of all. The weak force doesn't bind matter. It changes it. It's responsible for radioactive decay. the process by which one type of particle transforms into another. Without the weak force, nuclear fusion in the sun would be impossible. No stars, no heavier elements, no life. The weak force is carried by the W and Z bosons, which are very massive, nearly 100 times the mass of a proton. Because of their size, the weak force is short-range, operating only inside the nucleus. And yet, its effects reach across the cosmos, in the transformation of elements, in the glow of dying stars, in the delicate balance that gives rise to complexity. The Standard Model, physics master blueprint. Physicists have grouped all known elementary particles, matter particles, and force carriers into a framework called the Standard Model. It consists of 12 matter particles, 6 quarks, up, down, charm, strange, top, bottom, and 6 leptons, electron, muon, tau, and their 3 neutrinos. Force carrier particles, the photon, electromagnetism, gluons, strong force, W and Z bosons, weak force. And one more, the Higgs boson, which gives mass to particles via the Higgs field. According to the Standard Model, all matter and forces, except gravity, can be explained by these particles and their interactions. But there's a mystery still to solve. Why do particles have mass at all? The Higgs field, the universe's invisible drag. Imagine a room full of people. A celebrity walks in. The crowd gathers around, slows them down. Another person walks in, unnoticed, and passes freely. This is how the Higgs field works. It permeates all of space. As particles move through it, some interact more strongly and gain mass. Others barely interact and remain almost massless. The Higgs boson is the quantum particle associated with this field. Predicted in the 1960s, it was discovered in 2012 at the Large Hadron Collider, the most expensive and complex experiment in history. This discovery was monumental. It confirmed that particles acquire mass not by their own essence, but by their interaction with a universal field, a field that fills the vacuum of space. Where the model breaks. The Standard Model is one of the most successful theories in science, confirmed by decades of experiments. But it's also incomplete. It does not include gravity. It does not explain dark matter, which makes up 27% of the universe. It does not explain dark energy, which makes up another 68%. It says nothing about the origin of mass values or the relative strengths of the forces. And so the quest continues to find a theory of everything that unifies all forces, all particles, all aspects of nature into a single elegant framework. A universe built on relationships. What do we learn from this strange world of particle? We learn that the universe is not made of things. It is made of interactions. Matter is not solid and fixed. It is dynamic, relational, and often probabilistic. Particles are not billiard balls. They are vibrations in invisible fields, fleeting, shifting, popping into and out of existence. Space is not empty. It is alive with fields. Time is not absolute. It is bound to gravity, to motion, to mass. And we are not separate from this machinery. We are made of these same particles, governed by these same forces, born from the same field. The universe is not out there. It is within us, written in the language of quarks, leptons, bosons, and fields. And through the lens of physics, as Stephen Hawking shows us, we glimpse the elegance beneath the chaos, the order behind the stars, and the code from which all reality unfolds. But this introduced a new paradox. If black holes can evaporate, what happens to the information about the matter they consumed? According to quantum theory, information cannot be destroyed. But black holes seem to violate this sacred principle. This became known as the black hole information paradox, and it remains one of the greatest unresolved puzzles in modern physics. Hawking's work suggested that perhaps the information is encoded in the radiation itself, somehow preserved, even if in a scrambled form. Others proposed that information might be stored on the event horizon like a hologram, a radical idea that would later evolve into the holographic principle. This principle, championed by physicists like Gerard T. Hooft and Leonard Susskind, suggests that all the information inside a region of space may be described by data on its boundary, an idea with profound implications for the nature of reality. Black holes, once thought to be cosmic endpoints, became laboratories for testing the very limits of physics. They offer clues about the union of general relativity and quantum theory, a theory of quantum gravity that remains elusive. In recent years, black holes have stepped further into the spotlight. We have detected the gravitational waves produced by their collisions, ripples in space-time that travel across the cosmos. And in 2019, the Event Horizon Telescope captured the silhouette of a supermassive black hole in the galaxy M87, a shadow cast against a glowing halo of matter spiraling into the void. It was not a fiction. It was real. The darkness at the heart of a galaxy, framed by light, confirmed the predictions made by Einstein and expanded by Hawking. In that shadow lay a century of theoretical struggle and a triumph of human imagination. Black holes are no longer cosmic monsters lurking in the dark. They are keys to understanding gravity, time, and the structure of the universe. They connect the infinitely small with the infinitely large. They force us to ask, what happens at the edge of space and time? What lies beyond? For Hawking, black holes were more than just phenomena. They were symbols. Symbols of how the universe still holds secrets, waiting to be uncovered by bold minds. They challenge us not only to look outward into the depths of space, but inward, toward the limits of thought and the power of curiosity. In studying the darkness, Hawking found light. Chapter 9. The Arrow of Time. Time. We all feel its flow, a constant march from past to future, from what was, through what is, into what might be. But what is this arrow of time? Why does it seem to move in only one direction? In this chapter, Stephen Hawking addresses one of the most profound mysteries in physics. Why does time have a direction? Why can we remember the past, but not the future? Why do we grow older, not younger? Why does cream mix in a coffee, but never separate back? The puzzle of time's direction. The laws of physics, Newton's mechanics, Maxwell's electromagnetism, Einstein's relativity, even quantum mechanics, are time-symmetric. This means they work just as well if we play time backward. If you film two billiard balls colliding and then reverse the tape, you'd still be watching something physically valid. Yet our everyday experience tells us otherwise. Ice melts, but puddles don't freeze into intricate sculptures. Glass shatters, but shards don't leap back together. Clearly, something breaks the symmetry. So what creates the arrow of time? Hawking identifies three main arrows. 1. The thermodynamic arrow. 2. The psychological arrow. 3. The cosmological arrow. 1. The thermodynamic arrow of time. The second law of thermodynamics says that entropy, a measure of disorder, tends to increase over time. Imagine a jigsaw puzzle fully assembled. It's neat, ordered, low entropy. Now shake the box and let the pieces scatter. You've increased the disorder. The entropy and the chances of them randomly reassembling are astronomically low. This law gives time its direction. We don't see smashed eggs unscrambling or burnt logs reassembling, because those would violate the second law. Entropy is like a cosmic clock. It tells us which direction is forward. And yet, at the microscopic level, physics still doesn't care about time's direction. So the thermodynamic arrow must come from the initial conditions of a universe. That is, the universe started in an extraordinarily ordered state. The low entropy of the Big Bang set the arrow. Why it began that way remains one of the great unsolved questions. 2. The psychological arrow of time. Next is the arrow we live by. We remember the past, not the future. Our consciousness experiences time as a stream of unfolding moments, but only one direction. This arrow seems to align with the thermodynamic one. We remember events because they leave traces, increased entropy. For example, a book falls and breaks a lamp. The broken glass is evidence, disorder that encodes the memory of the event. But there's no such evidence of future events. They haven't happened yet. so entropy hasn't increased because of them. Memory is a process that relies on physical changes, neuron connections, chemical marks, even written records. All of them are entropic processes. So perhaps the reason we remember the past and not the future is simply because the past has more order. The future is undetermined, entropic, a space where probabilities rule, not memories. 3. The cosmological arrow of time. Finally, there's the cosmological arrow, the direction in which the universe itself expands. From the Big Bang to now, galaxies have been flying apart. If the universe ever reverses, collapses in a big crunch, would time reverse with it? Would entropy start to decrease? Would people live their lives backward? Hawking suggests that if the universe does collapse, the thermodynamic arrow might reverse too. But if that happens, would we notice? Maybe not. If entropy decreased, memories would as well. We might remember the future instead of the past. But from our perspective inside the system, everything would still feel normal, just reversed. It's a haunting idea. The past and future might be illusions shaped by entropy. Perhaps time's direction is a local condition, not a cosmic absolute. Time reversal in physics. Hawking also explores time reversal in quantum. The equations allow time to move forward or backward. Yet when we observe quantum systems, wave functions collapse. This collapse is irreversible. That suggests measurement itself might be the source of time's arrow. The observer, us, defines the direction of time through irreversible interaction with a system. In other words, consciousness may not just follow the arrow of time, it may help create it. So, what is time really? Hawking doesn't give a final answer. Instead, he invites us to see time not as a universal tick-tock, but as something emerging from the conditions of the cosmos, from entropy, from the expansion of space, and maybe even from consciousness itself. The past leaves its fingerprints. The future is an open field, but it is the low-entropy origin of the universe, the almost perfect order at the moment of the Big Bang, that makes it all possible. Without that, time might not flow at all. Closing reflection. So next time you feel time slipping by, in moments of joy or loss or quiet reflection, remember, you're not just moving through time. You're riding an arrow cast by the birth of the universe itself, one that emerges from stars and galaxies, from entropy and memory, from the very structure of reality. And yet, its final destination remains unknown. Chapter 10. Wormholes and Time Travel. What if the universe contains secret passageways, shortcuts through space and time? Could we, one day, step into a machine and emerge in another century? In this chapter, Stephen Hawking enters one of the most intriguing and mind-bending frontiers in theoretical physics, the possibility of time travel and the exotic tunnels known as wormholes. It's a chapter that doesn't just explore science. It stretches the limits of imagination, of causality, of reality itself. What is time travel? Time travel is not just the fantasy of science fiction. It is a serious question rooted in Einstein's theory of general relativity. General relativity tells us that space and time are part of a single entity, the fabric of space-time. And this fabric can curve, twist, and stretch under the influence of mass and energy. If space can bend, and time is part of space, then perhaps time, too, can loop back on itself. The central idea, if space-time can be warped just right, it might be possible to form a closed time-like curve, a path through the universe that returns to its own past. In other words, a route for time travel. But how would such a path exist? That's where wormholes come in. Wormholes, tunnels through space-time. A wormhole is a hypothetical tunnel that connects two distant points in space-time, like a cosmic subway system. If black holes are the universe's sinkholes, wormholes are its secret doorways. These were first imagined by Einstein and Nathan Rosen in 1935 in what became known as the Einstein-Rosen bridge. They considered the possibility that a black hole might be connected to a mirror version, a white hole, via a bridge through space-time. This bridge would bypass ordinary space, creating a kind of shortcut, instead of taking the long way around the universe. You leap through space-time itself. But there's a catch. The problem of stability. Most theoretical wormholes are unstable. They would collapse instantly unless held open by something exotic, a substance with negative energy density. This is not ordinary matter. This is something far stranger. Physicists call this exotic matter, and while it sounds fictional, there are hints in quantum theory, like the Casimir effect, that such negative energy might exist in small amounts. The Casimir effect shows that two uncharged plates in a vacuum can attract each other due to quantum fluctuations, creating regions of negative energy density between them. If exotic matter could be harnessed on a larger scale, perhaps it could hold a wormhole open long enough for someone, or something, to pass through. But this is still speculative physics, far from being proven. Wormholes and time travel. Now here's where things get really strange. If you could take one mouth of a wormhole and move it at near the speed of light, or place it near a massive gravitational source, time dilation would occur. This is a real effect predicted by relativity. Time slows down in strong gravity or at high speed. So one end of the wormhole ages more slowly than the other. Now imagine entering the wormhole through the younger end and exiting through the older one. Congratulations, you've just traveled backward in time. This isn't just a trick of clocks. This is a path that physically loops through space-time. The grandfather paradox. If time travel is possible, what's to stop someone from changing the past? The grandfather paradox asks, what if you traveled back in time and accidentally prevented your own grandfather from meeting your grandmother? You wouldn't be born, which means you couldn't go back, which means your grandfather lives, and so on. This loop of logic challenges our fundamental understanding of causality. To solve it, physicists have proposed several ideas. Novikov's self-consistency principle suggests that events in space-time are self-consistent. Any attempt to alter the past would be doomed to failure. You could visit the past, but you couldn't change it. Another possibility is the existence of multiple timelines or parallel universes. Each change in the past creates a new branch of reality. So killing your grandfather doesn't prevent your birth. It just shifts you into another universe where you were never born. But these solutions are theoretical, untestable, for now. Chronology protection conjecture. Stephen Hawking, despite his fascination with the idea, was skeptical about the practicality of time travel. He proposed what he called the chronology protection conjecture. This principle suggests that the laws of physics prevent time travel on macroscopic scales, ensuring that history remains consistent. According to Hawking, quantum effects near a wormhole might build up and destroy the wormhole the moment a closed time-like curve tries to form, acting like a cosmic safety switch. Why haven't we met any time travelers from the future? Perhaps because they simply can't get here. Or perhaps because they already have, and we just didn't notice. Quantum tunneling, virtual particles, and time loops. In the quantum world, particles can tunnel through barriers, appear and vanish, and even be entangled across space and time. Quantum mechanics, combined with general relativity, leads to wild speculations about particles moving backward in time, or virtual particles creating microscopic wormholes that flash in and out of existence in a vacuum of space. These quantum wormholes might connect different regions of space or even different moments in time, though only on subatomic scales. Could we one day learn to manipulate these tiny time loops? Could the ultimate computer, or civilization, one day grow a wormhole to human size? We don't know, but physics hasn't ruled it out. Time travel in popular culture versus physics. Science fiction often imagines time travel as a device, a machine, a dial, a DeLorean. But the reality is subtler. If time travel is possible, it is not through gadgets, but through the structure of space-time itself. Hawking reminds us, the laws of physics do not forbid time loops outright, but they might protect history from paradox. And even if time travel remains fiction, the physics of wormholes, quantum fields, and space-time curvature continue to reshape our understanding of reality. Closing reflection. So, are wormholes the key to time travel? Perhaps. But for now, they remain like the edge of a dream, supported by equations, yet unseen in nature. They represent our deepest questions. Is time linear or circular? Is the past fixed or fluid? Is a universe a place of cause or of possibility? Maybe we're closer than ever to discovering the truth. Or maybe the timeline is protected, so we never can. But as long as humans dream of traveling not just through space, but across time, the mystery of wormholes will remain one of the most profound and daring frontiers in all of physics. And who knows, maybe someone someday is already on their way back to tell us. Chapter 11. The Unification of Physics. Every age has its myths. For the ancient Greeks, it was the music of the spheres. For medieval theologians, it was the divine order. For modern physics, it is the theory of everything. A single, elegant equation that binds all the forces of nature, gravity, electromagnetism, the strong and weak nuclear interactions, into a unified framework. In this final chapter, Stephen Hawking takes us to the edge of human understanding, into the deep waters where science becomes almost indistinguishable from philosophy. This is the story of humankind's grandest dream, the complete unification of the laws of the universe, the fragmented forces of nature. In the universe we know, four fundamental forces govern everything. 1. Gravity, the weakest but the most far-reaching. It shapes galaxies, stars, and planets. 2. Electromagnetism, responsible for light, electricity, magnetism, and chemistry. 3. The strong nuclear force holds atomic nuclei together. 4. The weak nuclear force governs radioactive decay. Each of these forces works under its own set of rules, described by different theories. Einstein's general relativity for gravity and quantum field theory for the others. But here's the problem. These theories don't play well together. When we try to describe what happens in extreme environments, like the center of a black hole or the first moments of the Big Bang, the equations of relativity and quantum mechanics contradict each other. Our scientific map of the universe has two beautiful halves, but they won't merge. And so physicists began a quest to find a unified theory, a framework that explains all forces as manifestations of a single underlying principle. Unification, a historical dream. The idea of unification isn't new. In the 19th century, James Clerk Maxwell showed that electricity and magnetism were not separate phenomena, but two aspects of a single force, electromagnetism. That was the first great unification. Then, in the 20th century, physicists unified electromagnetism with a weak nuclear force, creating the electroweak theory, validated by particle experiments at CERN and other labs. This left three forces unified. Only gravity, massive, mysterious, and stubborn, remained apart. But gravity isn't just one more force. It is the geometry of space-time itself. To unite it with quantum theory requires rethinking the nature of space, time, and even information. And that's where things get truly profound. The challenge of gravity and quantum mechanics. Einstein's general relativity is a classical theory. It treats space-time as smooth and continuous. But quantum mechanics reveals a world of probabilities, uncertainties, and fluctuations. At very small scales, energy in space itself become grainy, frothing with temporary particles and fields. Try to combine these views, and the math explodes. Near singularities like the Big Bang or the core of black holes, quantum effects become extreme, yet gravity cannot be ignored. We need a quantum theory of gravity, but building one has proved fiendishly difficult. Numerous candidates have emerged, from loop quantum gravity to causal dynamical triangulations. But the most promising and ambitious contender has long been superstring theory, a glimpse of the ultimate equation. Superstring theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings of energy, each vibration corresponding to a different particle. In this theory, electrons, quarks, photons, and even the graviton, the hypothetical quantum of gravity, are all just different modes of string vibration. Space isn't four-dimensional, but 10 or 11-dimensional, with the extra dimensions curled up in tiny, hidden shapes. Strings are mathematically elegant. They naturally include gravity, and they offer the tantalizing possibility of a theory of everything. But there's a catch, or several. String theory isn't testable yet. The energy levels needed to observe strings directly are far beyond our current technology. And worse, there's not just one string theory. There are many. So many, in fact, that some physicists speak of a landscape of possible universes, each with different laws. Are we inching toward a final answer, or just trading one mystery for another? M-theory, the unifying framework? In the late 1990s, another theory emerged, M-theory, which unites all 5 versions of string theory into one higher-dimensional framework. M-theory suggests that strings are actually one-dimensional slices of even more fundamental membranes, or branes for short. This framework includes 11 dimensions, branes that might stretch across the universe, gravity and quantum fields coexisting, a possibility for a multiverse, infinite bubbles, each with its own physical laws. But M-theory is still incomplete. It is more a framework of ideas than a finished theory. We don't yet know what equations define it fully, or if it's the right path. And so the mystery deepens. The role of symmetry and simplicity. Throughout this search, physicists have followed a guiding light, symmetry. The universe, at its most fundamental level, appears to be governed by elegant, symmetrical principles, even if those symmetries are hidden or broken at larger scales. Einstein believed that the laws of nature should be beautiful, unified, and simple, not necessarily in their appearance, but in their essence. The unification of physics isn't just a technical problem. It's a philosophical quest for harmony, for a single rulebook that governs everything from galaxies to gluons. The universe is vast, but so is the power of a curious mind. If this video opened your eyes, even just a little, subscribe to the Tunnel of Sane, and let's keep exploring, because this is just the beginning.